Welcome back to the video lecture series of Digital Fundamental. Today we will discuss synchronous down counter. So let's start with the definition of synchronous counter and down counter. Here we have a synchronous counter. This synchronous counter is basically a group of flip-flops in which all flip-flops receive same clock signal. Okay, this synchronous counter means a group of flip-flops in which all flip-flops receive same external clock signal. That means all flip-flop will work simultaneously. That means parallelly. Okay, and here we have a down counter. This down counter means this counter which counts in a downward direction. That means it counts from large to small. Okay, this down counter is basically a counter which counts in a downward directions. That means from large to small, like n minus 1 and 3 2 1 0. Okay, so this is synchronous down counter. Now here this synchronous counter, to design synchronous counter, if we want to design n bit synchronous counter, okay, so we have to use n flip-flops. To design n bit synchronous down counter, we have to use n flip-flops having same clock signal which count total 2 raised to n values starting from 2 raised to n minus 1 to 0. Okay, using n flip-flops we can count a total number of value, that is 2 raised to n, and here this count is basically starting from 2 raised to n minus 1 to 0. Okay, so this synchronous down counter basically count in a downward directions and have same clock signals. Okay, this as this synchronous counter has same clock signal, so this synchronous counter is also known as parallel counter. This synchronous counter is also known as parallel counter because all flip-flops receive same clock signal such that all flip-flops will work simultaneously parallelly. Okay, that's why this synchronous counter is basically known as a parallel counter. Okay, now here in this synchronous counter we have to apply input values to count the sequence. Okay, in a synchronous down counter, whenever we want to count downward directions sequence, so we have to apply inputs in a such a manner that all flip-flops work simultaneously and counts in a downward directions. Okay, and here if we apply input, then whether our flip-flops works on a toggle mode or not, it depends on flip-flops input. Okay, it depends on flip-flops input that our flip-flop will work in a toggle mode or not. Okay, so if we want to design synchronous down counter, we have to apply a input value, but here clock signal are fixed for all the flip-flops. Okay, so let's discuss synchronous down counter with example. So here we have a 3-bit synchronous down counter. That means here we want to design 3-bit synchronous down counter. So to design 3-bit synchronous down counter, we have to use 3 flip-flops, right? And using this 3 flip-flops, we can count total 2 raised to 3, total 8 possible value starting from 7, 6, 5 to 0. Okay, so here how this 3-bit counters counts the sequence in a downward directions. So here we have this table. Okay, in this 3-bit synchronous down counter, our flip-flop will count in this manner. Okay, so here we have a initial value when there is a no clock signal applied. Here we have a 0 0 0. Then if clock signal apply, so first we have a bit, that is 1 1 1, then we have a 1 1 0, then we have a 1 0 1 and so on. Okay, so here we have a 7, 6, 5, 4, 3, 2, 1, 0, and again starting from 7. Okay, so this is basically a down counter. Okay, now for this is our desired sequence. That means we want output in a such a manner that it counts in a downward directions. So we have our desired output. Okay, this is our desired output using 3 flip-flops. Now if we want this kind of output, what are the input equations, or what are the inputs for this kind of sequence? So we have to calculate that values. Okay, so here we have our desired output. For this desired output, we have to find out value of input. Okay, so we can find out our input value from this desired output sequence by observing these values of Q1, Q2, Q3. Okay, so first let's observe this first flip-flops output, that is Q1. So here in this Q1, each and every times output will be toggled. Okay, here in this Q1 sequence, our outputs are in a toggle mode. Here every time input combinations, according to that we have this toggled operations. That means our first flip-flops is in a toggle mode, and to operate our flip-flops in a toggle mode, we have to decide our input, that is J1 K1 is equals to 1. Okay, because whenever we apply input that is equal to 1, so we have a toggle mode operations. So that's why we have a sequence of Q1 like this. If we apply J1 K1 is equals to 1. Okay, so this is our first flip-flops input, that is J1 K1 is equals to 1. Now for a second flip-flops input, we have to observe this Q2. Okay, so here this Q2 will toggle its state. Okay, here this Q2 will toggle its state, or basically change of its state occur when this Q1 is equals to 0. When this Q1 is equals to 0, this Q2 will change its state from 0 to 1 or 1 to 0. Okay, here also we have this toggle operation or change of state when Q1 is equals to 0. Here we have this Q1 is equals to 0, so again change of state. Here also when Q1 is equals to 0, change of state. So basically we can apply J2 K2 is equals to Q1 dash, because when Q1 is equals to 0, we have a toggle operations. So if we apply J1 K1 is equals to Q1 dash, so whenever Q1 is equals to 0, Q1 dash is equals to 1, and then J2 K2 is equals to 1, that means we have a toggle operations, right? So whenever we have a Q1 is equals to 0, basically in a JK flip-flops we have a input that is 1. So whenever this Q1 is equals to 0, we have this JK flip-flops inputs are 1 1. That means there is a change of state, basically a toggle mode operations when Q1 is equals to 0. That's why here we apply this Q1 dash, because whenever Q1 is equals to 0, Q1 dash is equals to 1, and such that if Q1 dash is equals to 1, this J and K is equals to 1 1, J2 K2 is equals to 1 1. So we have a toggle mode operation. So here we have using this input combinations, we have this sequence of Q2. Okay, whenever we have a flip-flops input like Q1 dash, we have this output Q2 will occur in this manner. Okay, so this is our Q2 sequence. Now if we want to calculate Q3, so we have to observe this Q3 table. Okay, so whenever this Q3 there is a change of state occur, here this Q2 and Q1 are equal to 0. Okay, both the Q2 and Q1 are equal to 0. We have a change of state. Whenever this both the value Q2 and Q1 is equal to 0, we have a change of states. Okay, here we have a change of states. Here also whenever this Q3 and Q2 are equal to 0, we have a change of states. That's why we can say that J3 K3 is equals to Q1 dash Q2 dash. J3 K3 is equals to Q1 dash into Q2 dash. So whenever we have a Q1 is equals to 0, Q2 is equals to 0, this Q1 dash and Q2 dash are equal to 1. That means if we apply Q1 dash into Q2 dash, so both 1 into 1, we have a 1 in a J3 K3. So due to this we have a change of state, or that means we have a toggle mode operation. So whenever this Q1 and Q2 both are equal to 0, we have a change of state. So using this three input combinations like J1 K1 is equals to 1, J2 K2 is equals to Q1 dash, J3 K3 is equals to Q1 dash into Q2 dash, we can calculate in a downward directions. We can calculate a downward directions down counter like 7, 6, 5, 4, 3, 2, 1, 0 and again 7. So using this logic we can design our 3-bit synchronous down counter. So here we have a logical diagram of 3-bit synchronous down counter. Here this 3 flip-flops are used because we want to design 3-bit synchronous down counter. Okay, so here we have a 3 flip-flops, and as here we have a synchronous counter, so that's why all flip-flops receive same external clock signal. All flip-flops have a same kind of external clock signal. That means all flip-flops will work parallelly. Okay, now here in a first flip-flop we have a input J1 K1, and according to previous value we apply J1 K1 is equals to 1 for our desired output of Q1. Okay, and in a J2 K2 we apply Q1 dash. So okay, here we have a connections from Q1 dash, and this value will given to this J2 K2. Okay, so using this input combinations we can find out our Q2 sequence, and here we have this AND gate because in a J3 K3 we have to apply Q1 dash into Q2 dash. So here we use one AND gate. So here we have a Q1 dash and Q2 dash, and this ANDing of this both Q1 dash and Q2 dash is connected to J3 K3. Okay, so here in a J3 K3 we have a Q1 dash into Q2 dash. So using this kind of logic circuit we can calculate in a downward direction. So this is our 3-bit synchronous down counter. Now how this synchronous down counter can count its values? So here we have a waveform characteristics of 3-bit synchronous down counter. Here whenever this external clock signal apply, according to that we have a Q1, Q2, Q3. Okay, all three output will work parallelly. Okay, so whenever this clock signal apply, first we have this initial value that is 0, because if there is a no clock signal apply then we have a initial value of our output is a 0. Okay, then here we apply negative edge trigger flip-flop. Okay, so here whenever this negative edge of clock arrive we have a change of states. Okay, so Q1 will change its state, or basically Q1 are toggled whenever we have a clock signal applied. So here we have this change of state continuously. Q1 is basically change its value 0 1 0 1 0 1. Okay, now here with this Q2 is in a toggle mode when Q1 is equals to 0. So here when this Q1 is equals to 0 we have a change of state. When Q1 is equals to 0 we have a toggle mode operations complemented value. Here also when Q1 is equals to 0 we have a toggle operations, and here also when Q1 is equals to 0 we have a toggle operations. So this Q1 will count its value and Q2 will count its value after this receiving values from Q1. Okay, so whenever Q1 is equals to 0 we have a toggle mode operations, and for Q3 whenever Q1 and Q2 both are equal to 0 we have a change of state. So here when Q1 and Q2 both are equal to 0 we have a change of state. Here also when Q1 and Q2 both are equal to 0 we have a change of state. So such that we can calculate values of Q1, Q2, Q3, and here we have a values like this 0 0 0, which is our initial value when there is a no clock signal. So initially we have a 0, then we have a 1 1 1. Okay, then we have a 1 1 0, then we have a 1 0 1, and so on. So this is basically 7 6 5 4 3 2 1 0, and again start from 7. Okay, so this is our synchronous down counter. So using this kind of logic we can design 3-bit synchronous down counter, or we can design any bit synchronous down counter using this logic. Okay, whenever we have this desired output sequence in a downward directions, we have to apply input like J1 K1 is equals to 1, J2 K2 is equals to Q1 dash, J3 K3 is equals to Q1 dash into Q2 dash. If we have a next flip flop, fourth flip flop, so we have a input like J4 K1 is equals to Q1 dash, Q2 dash, Q3 dash. Okay, so this is how we can design 3-bit or any bit synchronous down counter, and this is how this synchronous down counter works. Thank you.